Today is a very exciting lecture because it's the culmination of many of the concepts that we've been learning over the last couple of weeks. The last lecture, we derived the 1D heat equation using a shell balance. A couple of weeks ago, we learned about the Fourier series. Today, you're going to see, after we do an actual problem, how important the Fourier series is in developing a solution to the heat equation. So let's do a problem, an actual practical problem. Suppose that you have a slab, some kind of material. It might be a polymer film, it might be ceramic, some kind of solid material that varies along a one-dimensional direction x that varies between position x equal to 0 and x equal to L. So the material has length L. It's laterally insulated along the y direction, so there's no temperature variations along the y. And initially, there's some initial temperature distribution at time t equals 0 that is a known function of x. So f as a function of x. You know what this function is. It's given to you. You've made prior measurements as an engineer, the temperature profile inside your polymer film, you know what that is. It varies as some function of x at initial time. Now, at time t equals 0, you take both ends of the slab and subject it to 0 temperature. An ice bath, for example. You take both ends, dunk it into an infinite reservoir of ice bath. So the goal of this problem is to figure out how the temperature inside the slab varies as a function of position and with time. So I hope you understand the basic premise of the problem. You have some material, it's got some initial temperature distribution. Some places might be warm, some places might be hot or cold. There's some variation along the material. Boom, at time t equals 0, you subject both ends to freezing cold water. So those temperatures are going to drop to 0, and you want to figure out what happens to the temperature profile inside this material as a function of position and time. Now, when you think about it, if you wait a very, very long time, infinite time, you would expect the temperature profile inside the material to decay. So your initial known function f of x will go away and disappear. And eventually, the entire material will be at 0 temperature, right? 0 C all the way across, because of an infinite reservoir, an infinite sink of heat at both ends. So whatever heat that the material initially had will get absorbed by both ends, and you'll get 0 temperature all the way across. That would be your equilibrium temperature distribution at infinite time. But our goal is to figure out how it gets to equilibrium. Initially, you're going to subject it to some non-equilibrium condition. You got temperature distribution. Boom, you change the temperature at the ends. It's non-equilibrium. It's going to relax slowly away to 0 temperature everywhere at equilibrium. We want to capture this decay, this transient decay process out to equilibrium. By the way, do you know the difference between steady state and equilibrium? Equilibrium is when nothing is changing with position and time. Steady state means nothing is changing with time. You can still have things changing with position, but it's not varying with time. It's an important distinction to make as an engineer. All right, so we like to solve this problem. And like we derived last time, we're going to use the 1D heat equation that's written right here. Left-hand side is a partial derivative with respect to time. First derivative in time. On the right-hand side, we have a material constant called the thermal diffusivity, alpha. It tells you how conductive the material is to heat. And then you have a second derivative with respect to position. And that's the diffusion term. All right, so we have one derivative in time and two derivatives in position, which means that if you think about it from a straightforward perspective, you're going to get one constant of integration in time, just because we have one derivative in time. You get two constants of integration in position, right? Think back to your time as solving ODEs. You integrate twice in position, you're going to get two constants of integration. Therefore, we have 2 plus 3 total constants of integration, so to speak, that you would need to find in order to completely solve this problem. So you need 3 constraints of some kind. Well, the first one I've already given to you. The initial temperature distribution at time t equals 0 is some known function f of x. That's called our initial condition. It's initial because at time t equals 0, you know the temperature distribution inside your material. Initially, you know what it is. Initial condition. The other 2 constraints are called boundary conditions because you know the temperature at the boundaries across all times. So in this particular case, I'm telling you that you have a slab, you're subjecting both ends to a fixed known temperature of 0 temperature on both ends. So you have one condition, your initial condition, second condition, which is your boundary condition, and then your third condition, which is your boundary condition on the other end. Let's write those down. Just like this. We have an initial condition, time t equals 0. It's some function that you know as a function of x, and then boundary conditions both clamped at 0 temperature. Okay, so we would say that this problem is well posed. You have a governing equation for your temperature profile and 3 conditions that tell you the 3 constants of integration that presumably will come out as we solve this problem. Now, as you've seen already in this class, we solve differential equations by guessing. That's just how it works. We solve differential equations by giving a good guess. And now for this particular problem, we're going to make one major guess that will help us make a lot of progress. And that guess is that this temperature is a function of both position and time. T, x, comma, little t, time. We're going to guess that this can be written as a product of 2 functions. One function only as a function of time, one function only as a function of position. Let's write this down. Just like this. We have a temperature, which is in general a function of position and time. We're going to write it as a product of capital X, which is function of only the position x along the 1D coordinate, times another function, theta, which is only a function of time. So we are separating the 2 independent variables. One function that only depends on space, x, and another function that depends only on time, t. And the product of those 2 functions will give us the temperature profile. Like I said, it is a guess. It may not work after all. And in some problems, it won't work. In this particular problem, it will. And this is called separation of variables. So what we're going to do next is to substitute this guess back into our original partial differential equation and see what happens. We're just directly substituting this guess of separating the temperature profile into a product of 2 functions directly into the 2 expressions here coming from the original heat equation. Now, this left-hand side is a time derivative of these 2 functions. This capital X is only a function of position x, and therefore it can come outside the derivative. Same thing with the right-hand side. This function theta is only a function of time. Outside here is a partial derivative with respect to position x, and therefore this is a constant with respect to x, and it can come outside the derivative. Now next, we're going to divide the entire equation through by alpha, theta, and capital X, and simplify. You get the following up here. Again, all I've done is to divide the entire equation by alpha, x, and theta, and you arrive at this expression directly from this lower left-hand corner. Now, when you take a look at this equality, everything here on the left-hand side is only a function of time t, right? Because theta is a function of t only. That's what we guessed. Alpha is just a parameter. It's just a number, thermal conductivity of your material. So it's just a constant. It doesn't depend on anything. And this derivative is still just a function of time. So this left-hand side is only a function of time. The right-hand side in contrast, is only a function of position x. Therefore, you have to think about this a little bit. How could you ever have a situation where a function of one independent variable, time, is equal to a different independent variable, x? When you think about what could possibly be true, I mean, for example, t to the fifth is some function of time. But if I have square root of x, which is also a function of position, right? This is a function of position, function of time, but they are not equal to each other. And you could try to imagine any function of temperature or of time on the left, position x on the right, and think about when can they possibly be equal to each other for all time and position. You can't just get lucky for a specific value of time and position. For example, if you had time t equal to 2, you would x to the 5, or 2 to the 5th, and then you can maybe say, well, if a certain position at x such that it equals exactly that, okay, you can get the equality true. You can't do that. This equality is true for all positions and time. When can this ever be true? Think about it a little bit. So clearly, these things clearly cannot work. The only situation where this can be true is if both quantities are equal to a constant. If they're both equal to a constant, then they could be equal to each other. And for reasons that I'll explain in a little bit, I'm going to call it to be a weird constant, negative lambda squared. So once again, you have an equality here that can only be true if they're both equal to a constant. And that constant I've called lambda squared, or negative lambda squared. And I'll tell you why I've put the negative, and I'll tell you why I put the squared. You can call it constant c if you would like to. C on the right-hand side, and you can carry that solution through, and you'll get the same answer. This is mainly for convenience why we put the negative, and convenience why we put the squared. You'll see in a little bit. But the main point here now is that you have two ODEs to solve. First, you have this ODE, which is the time derivative of your theta equal to a constant. That's an ODE. It's a first order ODE. And now you're very good at solving those. You also have another ODE. What I underlined in blue is this spatial derivative term also has to be equal to a constant. So now what we've done is we've taken a partial differential equation and we've broken it down into two separate ordinary differential equations. And this is why it's so important to know how to solve ODEs. In many solutions to PDEs, it just comes down to solving a set of ODEs. So you solve ODEs to solve PDEs. That's why solving ODEs and knowing which tool to use and which branch to go to, it's incredibly important, because if you can't solve ODEs, you can't solve PDEs. So let's solve these two separate ODEs. We have an ODE in time and an ODE in space. Let's solve them both. Here's the first ODE. 1 over alpha theta times d theta dt time is equal to negative lambda squared. This is just a first order separable ODE, things that we like to hear. The solution to this first order separable ODE is just given by the following. It's just an exponential, some constant of integration a times e to the negative lambda squared alpha and time little t, right? Just go through it. You get this, a log on the left-hand side, you get a negative alpha lambda squared t plus some constant. You take the exponential on both sides, and then out comes the solution. Pretty easy stuff. You're an expert at solving these now, so I've skipped a couple of steps. Okay, so now here's one of the reasons why we chose negative lambda squared. The negative sign carries through down here. So remember that this theta accounts for the time part of your temperature profile. So the fact that this, as your time t grows, means that this theta function will decay exponentially quickly, which makes kind of sense, right? Intuitively, I have some initial temperature profile, f of x, running across the slab. It's going to be 0 temperature on both with the boundary condition. It will decay as a function of time. So you want that to happen. Suppose you didn't choose negative lambda squared, but you instead chose a positive lambda squared. Then you get a positive number here, and then in your exponential, you'll have e to the positive alpha lambda squared t. That would be really aphysical, because that would say that as you wait in time, your theta, or in other words, your temperature, will be exploding exponentially quickly. So you'll have a temperature inside your slab that grows to infinite degrees Kelvin as a function of time, which can't be true. It's aphysical. Therefore, we're going to choose the negative sign to ensure that it makes physical sense. So the temperature decays as a function of time, which is what you expect physically. So that's the first reason why we've chosen negative sign out in front of the constant. Now, this is our time ODE. This is one of the two ODEs. Let's solve the other one, because here we have a space ODE to also solve. Let's do that next. All right, so here's the other ODE that we need to solve. We have a space ODE, which I've just written down straight down here. I've just multiplied through by capital X, and now we have the following ODE to solve. It's your second order, constant coefficient, linear, homogeneous equation. Words that we love to hear. It's like music to our ears when you see linear, constant coefficient, homogeneous. Great, I know how to solve that. Very easy. You'd use your characteristic equation. In this case, you'd have your roots be equal to plus and minus I, the imaginary unit, times lambda, right? Go through the calculation. You get your characteristic equation, your roots. You'll get imaginary complex roots. I times lambda. Okay? So you get complex roots, and like you already know how to do, when you have complex roots, your solution to the second order ODE will be sines and cosines. Just like that. So you have two constants of integration, b and c. It's multiplied against a cosine and sine, because that's what you get when you have complex roots. Now, going back to why did I choose negative lambda squared? I told you why I chose the negative, because it needs to make physical sense. The lambda squared part is just, again, for convenience. When you come down here, I have a cosine of a lambda, because you take the square root when you take the roots of the characteristic equation, and so I just have cosine of lambda x and sine of lambda x. If you didn't have the squared up here, you would just end up with a square root of lambdas down here. That's perfectly fine. If you would prefer to write that instead, you could just leave this up here without the squared, and you would just get a square root down here and move on. You get the exact same solution. It's just for convenience that it's just better and easier to just have a lambda linear down here. So that's why we squared it up there. So that's why the negative sign is for physical reason. The squared is just convenience. Okay, so at this point, we've made a lot of progress because we've taken this PDE, guessed they could be separated into product of x and product of time functions, plugged it into the equation. Now we have two separate ODEs that we can very easily solve. And now, presumably, we can just multiply this theta function and this capital X function, put them together, and that's going to be our solution, right? It's the product of these two functions. Presumably, that should give us our temperature profile. So let's write that down and see what we get. Okay, I've erased a couple of things. I erased everything up here because we don't need that anymore. We found our two solutions, one for theta as a function of time, one for capital X as a function of position x. I've taken those two products together and wrote it down here on the bottom left. I have a temperature profile, which is a product of these two functions. I've plugged it in, and you get theta, and you get capital X over here on the right. Now I'm going to make one minor edit to this term here, where I have a constant a standing out in front That's the constant of integration that came from the time ODE. And I'm just going to multiply that across to the b and c terms on the right, because a and b and c are all constants of integration, so they're just numbers. So a times b is still a constant, a times c is still a constant. So I'm just going to rewrite it and absorb the constants inside the bracket. All right, so I've just called them d and e instead. So d would just be a times b, e would be a times c. All right, so now we have three unknowns inside this equation. We have constants of integration d and e. We've also introduced this other one, lambda, where we also don't know what that is. It came from up here of setting that equal to negative lambda squared. So we actually kind of introduced another unknown in that separation of variables process. So we have three unknowns still here, but luckily we have three conditions, the initial condition and two boundary conditions. So let's first apply the boundary conditions to see if we can make some progress on understanding either d or e. So let's use the first boundary condition up here at x equal to 0. On the left-hand boundary, it's fixed at 0 temperature. Let's apply that boundary condition and see what happens. So all we're going to do here is plug in x equal to 0 in this temperature profile that we now have for all time t. Set that equal to 0. That's a boundary condition. So now let's do that. OK, we get this. So now we have sine of 0, which we know is equal to 0. So that term goes away completely, because sine of 0 is identically equal to 0. And cosine of 0 is equal to 1. Therefore, we have constant d times this exponential decaying function must be equal to 0. That must be true because it's a constraint, a boundary condition that must be obeyed for all time t. So this term over here can never be equal to 0 for finite time t, right? It's just exponential decay. It's going to have some number even at very, very large time. So the only way that we can make this true is if our coefficient d is equal to 0. D being equal to 0 allows us to satisfy this boundary condition. So coming back over here, what this constraint gave us is that the cosine terms all die. It's just completely gone. So the d terms all die, which means cosines are not a part of the solution. All we know is at best, it will be a function of sines. We still don't know what e is. We still don't know what lambda is. So let's apply the next boundary condition at x equal to the right-hand end at x equal to L, see what that gives us. Maybe it'll give us something about e, which might be reasonable for you to expect. We get this. Again, just plugging in this equation with x being equal to L. I'm not even bothering with the cosine term because d is 0. So the cosines we don't have to worry about anymore. So only the sines, e, and then the usual exponential time decay out in the front. All of this must be equal to 0 for all time t. So you stare at this for a little bit. And the obvious thing that you might think about is, oh, well, e must be 0. After all, up here, we set d equal to 0, and that's the way we satisfy the boundary condition. So maybe e must be 0. If that's true, then surely we satisfy this boundary condition. But when you think about it, if d was 0 and e were 0, then you go back into here, and also then the sine terms would go away. So then you get t is equal to 0 temperature all the time, everywhere. And that's not right. That doesn't satisfy your initial condition. Your initial condition says that at time t equals 0, it must be f of x. And it's just weird that the temperature is 0. You just get the trivial solution for all time t and all position x. It just doesn't seem right. This is called the trivial solution. So d being equal to 0, that's fine. But if e were also 0, it gives you the trivial solution. We don't want that. So let's go back up to here and think about, is there any other way in which this condition could be true? This exponential term on the left, we can't make that go to 0. exponential decay function, that's not going to go to 0. We can't make that go to 0, so there's no hope here. E, we already just found that we can't really do much with it, because if it's 0, then it's game over. So then our last hope, our ray of hope, is sine lambda L must be equal to 0. Now when you think about it, a sine function looks something like this. And it actually does equal to 0. Here, 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 here. And what values are those? When it's equal to pi, 2 pi, sine pi, 4 pi, dot, 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 right? So when they're integer values of pi, sine crosses the y-axis. Therefore, if sine of lambda L, where lambda L were pi integers, then yeah, sine does equal to 0 at those values. Let's write this down. So this boundary condition will be true if the argument inside the sine, lambda times L, the size of the domain, if that was equal to n times pi, where n takes on integer values, then absolutely, because you would just have sine of n pi, and sine of n pi is equal to 0. But what this means, though, is that we have an infinite number of ways in which we can make this boundary condition be true. N could just be 2. If n is 2, then we have lambda L is equal to 2 pi. That would correspond to this point right here, where indeed sine of 2 pi is equal to 0. But you're kind of ignoring all the other ways, all the other combinations in which this can also be true. What this suggests is that there are many, many possible solutions. In fact, an infinite number of possible solutions in which this boundary condition could be true. And because there are infinite number of possibilities, I've added an index n below the lambda to indicate that there are many values, infinite many number of values of lambdas to make this condition come true. And I've rewritten it as lambda n is equal to n pi divided by L. Now, this is called the eigenvalue. Now, think back to your vector calculus class. You learned that vectors could be, you can have orthogonal properties, you can have eigenvectors, you can have eigenvalues of vectors and matrices. Like we already saw with orthogonality, functions can be orthogonal. Functions can also have eigenvalues and eigenfunctions. This is called an eigenvalue of this function. Okay, so now, boundary condition number 2, we thought would give us the value of E. It turns out it didn't, but instead it gave us the value of lambda. So let's recap for the moment, right? We have initially 3 constants of integration, A, B, and C. A that came from the time ODE, B and C that came from the space ODE. But during that separation process, we introduced another unknown called lambda. We were able to absorb A and B into D, and then A and C into E, but we still had D, E, and lambda as unknowns. We used boundary condition on the left, boundary condition number 1, to give the value of D. The other boundary condition on the right, we thought would give us E, but it didn't. It gave us the value of lambdas instead. So now we know D, we know what the lambdas are. Okay, and while we're at it, we need to make sure that we capture all possible solutions. So this is going to become lambda n, because we can have, again, many possible lambdas in which this could be true. But if we can have many combinations of sine lambda n, sine n pi over L, that means that there are many modes, many frequencies, many different types of sines that we can all add together to create our overall temperature distribution. Now, this is sounding a lot like the Fourier series. We're getting a flashback to what we just did for the last couple of weeks. The Fourier series is all about that. It's taking a bunch of different sines and cosines, building up our function in the right way with the right amplitude, E, such that we can build our full function temperature profile. So what this implies is that there should be many different weights E sub n corresponding to each sine index, n of 0, 1, 2, 3. For the case of sine, n of 0 doesn't really give you anything because sine of 0 is 0. So usually with sines, the index starts at 1. That's a technical detail. Let's not worry about that. But the point is, now we have a coefficient E sub n that we now need to figure out. But we have one last condition that we haven't used yet. This one. So our initial condition will give us the value of E sub n. So let's write that down. We're almost there. I know it's a long problem, but we're almost done. We have our last condition, our initial condition, right here. Just brought that up and wrote it on the upper right. Now, one more thing that I wanted to add. I showed you earlier that we're going to need many different indices n, or modes, where we can build up our function. Again, that sounds a lot like a Fourier series. And here, now that we've added our index n, our total solution is the superposition of all of these possible sine modes and frequencies. So let's add a summation out in the front to indicate that the total solution is a superposition, a summation of all of these integer values of n. Just like that. So now you have a sum over n going from all integer values of this exponential decay. We now know what lambda n is, so that's no longer an unknown. We know what that is, times en sine lambda nx. Now we can plug it into this expression and see what happens. All I've done is to set time t equal to 0, and therefore the exponential prefactor goes away because e to the 0 is 1. And so all that's left is the summation from all integer values, 0 all the way to infinity, times e sub n sine lambda n, which is n pi over L times x. All of that is equal to some known function f of x. So if the Fourier series hasn't flashed through your head, you need to restudy Fourier series again, because this is right in front of us. This is the definition of the Fourier sine series. We have some known function we're trying to model. We're adding together many, many, many sine frequencies of n modes with their respective weights. So we know exactly how to obtain the coefficient E sub n using orthogonality from Fourier series. Just like that. This is using the definition of orthogonality. You multiply both sides of the equation by sine m pi x over L, like we did in the first class of Fourier series. You go through all indices, they're orthogonal, so all the signs cancel, except when n and m are the same, boom, out comes one term that you're able to pick out. And it's equal to 2 over L, integral of 0 to L of this integral. Now, this factor of 2 comes out inside because we're integrating over half the domain. Remember the odd and even extensions that we did for the Fourier series? And I told you that a lot of times you won't need to worry about which one to choose, because a lot of times the problem will determine it for you. This is the situation here. We're taking an odd extension because there's a sine series inside this integrand. Therefore, you're taking this Fourier function f, extending it as an odd function from negative L to L. Because in this problem, the domain goes from 0 to L, we need to extend the Fourier series from negative L to L, because Fourier series is defined on a periodic interval from negative L to L. Therefore, we're going to do an odd extension, and we're getting a factor of 2 because we have double the area now, and you get this coefficient to come out. Okay, so we're done with our problem. Let's write down our final solution. And there we have it. We have our temperature profile, which is a function of position x, and time is a summation over all indices n of some coefficient E sub n, which we know up here from using orthogonality in the Fourier sine series, times an exponentially decaying function where it depends on the thermal conductivity and thermal diffusivity alpha, and you have your eigenvalues n pi over L times the time t. And lastly, you have sines n pi x over L multiplied there. This is it. This is the temperature profile of your material with some initial temperature distribution f of x that decays out to 0 as you wait infinite time. Now, I think mathematically some of you might be able to follow what's going on, but honestly, when I first saw this, I was just so overwhelmed at how complicated everything is. It just seems like gibberish, mathematical gibberish, and just so many things, like summations, weird integral function f, indices n. It just, everything seems so strange and weird. All right, let's actually plug in a real function, and I wanted to show you on MATLAB how this temperature profile actually looks spatially using pictures and profiles. Because for me at least, I learn a lot when I'm able to connect the mathematics to an actual physical process that I can touch and feel and see. And when I can see a temperature profile and look at its decay and how each piece fits together, that really helps my understanding. So let's take a look at this solution to the 1D heat equation for the special case where we have some known function of f of x. This is our solution to the 1D heat equation. That's amazing that now you're able to solve this really complicated partial differential equation, and all you had to know was know how to solve ODEs. That's all you needed to know. Let's do an example case for the special case of the function f of x being equal to the linear function x. Okay, let's do an example in the situation where f of x, which is our initial temperature distribution, f of x, is a concrete example where it varies linearly as a function of position. So at x equal to 0, it's already cold initially, and then the temperature goes up and up and up and up and up as you move from left to right. And as you get to the boundary, it's very warm. It's at temperature, in this case, L. So very cold on the left, ramps up, becomes warm linearly at the right boundary, and then at time t equals 0, boom, you're going to take both boundaries, quench it to 0 temperature, and you're going to see how this temperature profile evolves as a function of time and position. Let's go over to the MATLAB screen and see what this looks like when it's solved numerically. So over here in the MATLAB script, we've done exactly that. So what we have here is a 1D heat equation solution of our pen and paper calculation translated in code. What we have first is this term right here, which is the coefficient that we just calculated. We have E sub n is equal to 2 times the integral of the function f of x, which in this case is just equal to linear x, times sine of n pi x integrated between 0 and L, which in this case I've set to 1. So if you come back up here, you see that there is a length scale L, which in this case I've just set to 1. You can choose whatever L you want. For convenience, I've just chosen to be 1. So going back down here, it's technically 2 over L, 2 over 1, integral of x times sine n pi x over L, which is 1, integrated between 0 and L. Okay, so this is exactly a literal translation of the Fourier coefficients that we calculated up here. The second line is our definition of lambda, and we've absorbed this alpha inside. So we've said that lambda is equal to n pi over L over 1 squared times alpha. So we've just put the alpha inside the definition. We've also taken the square. That's a minor detail. And this last line right here is E sub n times sine n pi x over L times exponential of negative lambda times t. So this is literally what we have up here. E sub n, which we just defined earlier, exponential, negative lambda times t, times sine n pi x over L. That's exactly just translated in MATLAB code. And finally, to capture the summation, we just added a function here, u underscore xt, which keeps track of our temperature. And you can notice we're adding it. We're adding to this value more and more values of each index n. So there's a for loop outside that sums over all the index values from n going from 1 all the way to terms. That's the total number of terms. Like I said, with Fourier series, you don't practically go out to infinity. You cut it off at some finite value of n. It goes out to the number of terms. Down here, I've defined the thermal diffusivity, 10 to the minus 2. I've defined my domain, discretized it, and I'm going to take snapshots at certain values of time points, from 0 all the way out to time point of 30. And lastly, for this example, I've taken 30 terms in the summation for the Fourier series. So let's evaluate this. The plot looks something like this. What I'm plotting here on the y-axis is the temperature profile, T, x comma time. And on the x-axis, I'm plotting the x position, the 1D position along the slab. Now, the different colors indicate different time points of the temperature profile. The black line you see back there that you can barely see because it's buried under all the other curves is the initial condition. You can see this black line is f of x is equal to x, the linear ramping function where we said that initially on the left-hand side it's cold, it gets warmer and warmer and warmer as you reach the right-hand boundary. That's exactly represented here in this black line going from 0 all the way out to the boundary value. Now, when you take one time step to 0.01, shown in blue, you can see that immediately the boundary value goes to 0 on both ends. And that must be the case because up here we've put in a constraint, a boundary condition that said that at x equal to L and x equal to 0, the temperature must dive down to 0 at time t equals 0 plus. So the initial condition that was warm up here at x equal to L immediately has to plunge down all the way to 0. And you can really see that the Fourier series in blue over here in the curve is wiggle, 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 boom, it has to go all the way down. And that's why you see a little bit of the Gibbs phenomena-like situation happening here, where it's trying to take a very high frequency mode and trying to plunge it back down to 0 as fast as possible, while also capturing the linear function of the slope, f of x is equal to x. That's why you see the wiggles closer and closer as you get to the boundary. Now, the orange curve is a little bit later in time, t equal to 1. A little bit later, t equal to 4, t equal to 10, t equal to 30. So you can see that as you wait in time, the temperature just dampens, relaxes, and at time, long time, the temperature will just become a steady profile at 0. You've reached equilibrium. So the time progression in this plot is read as black to blue to orange to purple to green. That's the progression of time. And you're seeing that heat is initially very high along the right-hand side, that's the warmest, and that heat gets dissipated into the infinite bath, the reservoir of ice bath set at 0 temperature on both ends. And the right-hand lobe down here is decaying more slowly, of course, because the right-hand side has more heat and energy stored there initially, and it gets lower and lower and lower as a function of time. So that's why it's kind of an asymmetric profile on the right-hand side that decays as a function of time. But what's really cool about this graphical illustration of this solution is that for me, it finally clicked. When I learned this for the first time and I saw the actual profile, everything clicked for me that why there is an exponential decaying term. That term is the thing that's just dampening everything down to 0. So you have all these wiggles from the initial condition that just gets dampened and it relaxes slowly to 0, exponentially quickly. So that makes a lot of sense. And the E sub n and sine n pi x over L is just the Fourier series that's needed to build up our function from our initial condition of f of x is equal to x all the way as a progression in time. So there are summations everywhere in this profile. You just see it most pronounced at the initial condition because you're trying to approximate this linear function. It has to go boom all the way down, and so you see the ripples most accurately there. But again, this is a case for only number of terms equal to 30. If I were to go back here and change this to 50, the computer is going to take a little longer, but it's going to get the solution. You can see that now the solution is much more crisp and clean, but you can still see that there's a little bit of wobble down here. It's trying really hard to capture this initial condition, but boom, it goes all the way down. So of course, if you take more terms, the more accurate your solution will be, but your computer is going to take a little bit longer because it's doing more summations. Okay, so I thought, again, this was such a cool application of actually seeing all the mathematical gibberish and weirdness and summations and E sub n's and everything when you can make that connection to a physical phenomena. To me, that's when I felt like I really understood the mathematical language. You can always do the math and you can make progress, but connecting the technical math to the physical phenomena in the process that you're trying to engineer or trying to understand fundamentally is really what it takes to make the connection from the details all the way to predicting and controlling material properties. Now, hopefully you also got a sense of how important the Fourier series is. It is such an incredible tool. It can do image analysis. It can be important in making progress to solving the heat equation and predicting temperature profiles in reactors and heat jackets and fluidized beds, bioreactors. It's an important concept to know for science and engineering. And in fact, starting with next lecture, we're going to consider different types of boundary conditions. And you'll see again, Fourier series will come to our rescue. All right, let's end here. I hope you have a wonderful day, and I will see you next time.